Goedemiddag allemaal en ja, welkom. Ik ben Isabel Van de Wayenberg, ik werk bij Flanders Make en vandaag wil ik jullie een stukje meenemen in het verhaal rond reversibel verlijmen of debonding on command, debonding on demand. Het is een hot topic de laatste jaren en ik hoop dat ik jullie de komende half uur een beetje kan inspireren met technologie daaromtrent. Ja. Eerst zou ik even willen toelichten Flanders Make, wie zijn we precies. Maar dan ga ik helemaal into de content verlijmen. Ik ben trouwens bezig in het Nederlands. Is het Nederlands oké voor iedereen? Of does anyone prefer English? Then I switch to English. Just English, no problem. We just switch. And then I will go into the context of advantages and challenges within adhesive bonding. And reversible bonding, what is reversible bonding? I will show you also some demonstrators that have been integrated. Of course, not every product at this moment is made with the reversible bonding technology integrated already. So what are we doing with classically bonded parts? How do we dismantle them? I will also give some examples on what we can do with them. And I will finish the presentation with an overview of expertise, but also running projects within Flanders Make that can be of interest as well. So first of all, some of you might know Flanders Make. We are one of the 4 strategic research centers in Flanders, next to Vito, IMEC and VIB. We also have a booth here on the fair, so if you want to come over and visit us, you're most than welcome. Flanders Make, we are mainly working with and for the manufacturing industry, but not only purely manufacturing industry, also non-manufacturing, for example, pharma industry that encounter manufacturing challenges. They are welcome to come to us to discuss possible research. We are situated over Flanders with 3 co-creation centers, and we are really working closely with the 5 Flemish universities as well. And the type of projects or activities you can do with us, these are really research projects or really customized innovations. Also, testing and validation is a possibility. We have a huge amount of infrastructure. So this is really in a nutshell and really high level, but it's giving you a flavor on what Flanders Make is doing. Now, when we come to adhesive bonding, I think most of you already know a lot of these advantages, why we should use adhesive bonding instead of any other joining technology like mechanical joining, riveting, bolting, or welding. With adhesive bonding, we can create a uniform stress distribution, unlike with mechanical bolting, for example. We can also achieve a weight gain because it's quite of a light solution, a light joining technology. Also, another advantage is that when we want to bond dissimilar materials without having risk on corrosion, also here adhesive bonding is a nice solution. On top of it, sometimes you have lots of secondary requirements like vibration damping, sealing function, electrical or thermal insulation. Also here adhesive bonding is quite of a good solution. But there are drawbacks as well, or challenges. An adhesive is a polymer, so just like a polymer, it can age, it can show degradation under influence of UV, under influence of moisture, temperature fluctuations. It has got a certain thermal sensitivity. And also to take into account during your process, we need time, curing time, drying time, before our components, our product is on full strength. Just something that you have to keep in mind. And quite often when we bond things in an adhesive, in an adhesive way, we bond it to be bonded permanently, so it's a structural joint. And how do we disassemble afterwards? This is quite often difficult. We damage the samples, we damage the product, and that cannot be the purpose, of course. So if we think about eco-design, and we know that within Europe there are lots of rules coming up about products that should be easily repairable, products that should be easily upgradable, well, then we could say, well, adhesive bonding, this is not a good solution. We go back to mechanical joining. But I hope with this presentation I can already give you some ideas and convince you that that is not necessary. So, reversible bonding, debonding on demand. First of all, the concept of reversible bonding is, we use adhesive bonding to join two components into a product, and we want them to last for a lifetime. They are structurally bonded, they stay intact, as long as there is no trigger active. So we also don't want to be have a dismantled product just whenever a certain temperature is reached without having control on it. But as soon as the trigger is active, something is happening that the components will be dismantled, will be debonded from each other. And if this is happening in the adhesive layer or on the edge of the adhesive with the component, that doesn't matter. It does matter that the two components do not have extra damage during this dismantling. So they stay as intact as possible. Of course, if you want to repair one of the components will already be damaged, but you do not add any extra damage. And then, of course, you have your two components. You can prepare them again, those two components, to be rebonded if you want to. That's why we call it reversible bonding. You can make it a circular process. And this can have a lot of advantages because you increase a bit the sustainability of your product. You make it possible for your product to be repaired whenever necessary. You can also make it possible to, for example, at the end of lifetime, when one of the components is already end of life, but the other component is still of high value and can be reused, you can dismantle that high value component and reuse it again. It can also happen, for example, during production when there is a misassembly. One of the demonstrators I will show is an example of a misassembly during production. And also when we talk about end of life and our waste streams, it's important that we can that we remain with a high value waste stream. So it's important that we have as pure waste streams as possible. Also here, reversible bonding or debonding on command can be an added value. And when we talk about these triggers to debond our components, we have, let's say, three categories of triggers that are possible. First of all, we have the mechanical trigger. I think this is quite straightforward. You just tear your parts apart, or you make a crack and you let the crack grow. You cut in between the parts. It's quite easy, straightforward, as long as your design is simple. So don't make it more difficult. If this is doing the job, it's good. But sometimes there is a little bit more technology involved, and we can use thermal triggers. Thermal triggers, we will play with the temperature. Quite often we increase the temperature above the glass transition temperature of our adhesive. And how we do it, it doesn't matter. It can be with convection, induction, infrared. But when we increase the temperature above the glass transition temperature, then our adhesive is coming weak and we can debond the components quite easily. And we can have an extra aid in this with thermal expandable particles. These are particles that we add to the adhesive, and under influence of temperature they will swell, and they will in that sense also apply a mechanical force on the bonding line, and they will let your components debond. This is still there is still research going on this, but it's high TRL research. And then we have electrochemical debonding, where we use electricity or UV light, for example, to degrade your adhesive and to make it possible to debond your components. This is rather low TRL research. This is existing on really small scale examples. Within Flanders Make, we are mainly focused and having quite some expertise on the thermal trigger technologies. So when we come to some examples, our first example that I want to show you is thermal debonding on a glass lens demonstrator. So for example, you have these projector lenses, and at end of lifetime, quite often these electronic components, they're really end of life, they're going to a waste stream, but your glass components, they are of higher value and they can be reused. They're not damaged yet, they can just be reused. So it would be good to see if there is a possibility to use reversible bonding in this example. And therefore we made a demonstrator based on a spherical glass, so it's not a flat glass, it's a spherical glass, glued on an aluminum carrier. And we use MMA adhesive together with these TEPs. When we put the complete product in an oven at around 120 degrees, within less than 10 minutes, you see it on the video appearing, within less than 10 minutes everything is debonded. So the product is just put on a certain mount. It's just their own force, their own weight that is debonding the complete product. You see that adhesive is being foamed up due to the particles inside it. It's a brittle residue that we have on the substrates that can be erased quite quickly, quite easily, and both of the components, without any damage, they can be prepared again for a new adhesive bonding if we want to. Also here, there was a risk, of course, that your glass and your aluminum have a too high difference in thermal expansion, that there would be too much tension on the glass and that cracks would occur, but this is not the case. So this is really a feasibility study on technological level, which is now in a couple of companies being tested to really be integrated in their products to get the high value Prisma glass recovered at end of life of the product as a whole. Another example I want to show is of much larger dimension. What you see here is a sketch of a bus, but this example could also be valid for trains, for trams, etc. So it's industrial automotive context. And what's happening there is a side panel. It's a glass fiber reinforced composite sandwich panel, which is quite of high value, and that is being glued on a metal chassis, a steel chassis. During production, sometimes this is meters and meters wide, and sometimes there is a misalignment. And the thing is, you have meters of adhesive that you have to apply, but sometimes your adhesive here is already starting to cure when you come here and you see there is a misalignment. So when you have to get rid of that composite panel, this composite panel gets damaged and it just purely wastes. Yeah. That's a pity, of course. It's money. It's from an environmental point of view. It's also a pity. It's labor hour. So we want to see, can we apply reversible bonding to be a solution for this problem? This was also part of a research project where VDL, the VDL company, delivered us a material. So it's really composite material, really used in reality. And also our partners, Vito, they made the calculations for the economic and environmental analysis as well. But first, for a technical point of view, and now I hope that this video will work. What we did here, what you see here, is a cutout of that composite side panel. So we didn't do the test on this what is it, 10 meters wide bus. Our lab is not that big. So this is a cutout of 2 meters wide. And you see that the white panel is glued on the steel beams. The black line you see there is the adhesive, polyurethane adhesive, mixed with just a low percentage of thermal expandable particles. And we use inductive heating to heat up the steel beams. That heat is being transferred to the adhesive bond line and will make the thermal expandable particles swell a bit, just enough for the composite panel to come loose from the steel chassis. So no external force is needed to achieve this, and this is achieved within 10 minutes again, or a little bit more than 10 minutes. It was 11 minutes. But also you can play a little bit with your settings, of course, of your induction heating. So we see that from a technological point of view, this is possible. But of course, is it also from an economic point of view interesting to do this? And also about environmental perspective, because this might be a nice circular solution fitting into circular economy, but is it really interesting? Our partners at Vito, they did these calculations, this fully detailed analysis. I will not go into detail now, but if you're interested in that, come and speak to me, because I can give you all necessary contact details to learn more about that. But I want to give you the results of this analysis. First of all, the environmental point of view. It's quite obvious when we do not have to make another composite panel, and when we can recuperate our composite panel, that we do, of course, from an environmental point of view, we have some benefits. That's true if we just look at the production of that side panel. But if you take into account the complete bus, then there are much more severe other factors. The production of the batteries, the production of the motor, this is much more severe than the composite panel. So maybe this was not the wow solution or analysis that we wanted to hear, but that's just reality. From an economic point of view, it's also important. We thought, of course, you will not have primary production again of your composite side panel, so it's a saving that you can do. But you have to take into account how many times does this error occur in your production, and how valuable is your composite panel. Is it a very expensive panel, or is it somewhat cheaper? That will all have influence on the result. Within this specific example, we've seen that after 6 years, there is a return on investment. It's becoming really interesting to use this technique, because you also did, of course, investments in changing a bit of your infrastructure. You have to change your glue dispenser, and maybe you have to change a little bit in your infrastructure to make it possible to debond again. So you have to take all these figures into account, which means, as I said, for this specific example, this was an interesting solution. It can be integrated, but we have to look at it case by case, and it depends on your production process and on your circumstances. Now, many of the parts that are now in use, they're coming end of life, and we also want to debond them without losing our components. How can we deal with this? Well, there is an example from automotive industry. You might know it already. When you want to debond your windshield, your front windshield of your car, they use a kind of a thread cutting to debond the parts. That's a possibility. As I said before, when your design is quite simple and not too complex, this will do the job. It's quite straightforward, and it's just good. So this is always something you could apply. Within Flanders Make, we are also currently doing research on, at this stage of the research, we are mainly focusing on battery packs, where also the design is quite simple. But we're doing research to see what we can do to debond these kind of things. I will, I think, Here, you can see it. So you have this kind of multi-tool equipment that you can use to get to debond the top cover of the complete assembly. It's straightforward. These are just flat surfaces. It's going quite quickly, quite easy to do. What you see is there is still some adhesive residue on the surfaces. That's something you want to get rid of course, afterwards as well. So what we're investigating in this project is not only within one of the next stages to go to complexer designs, but we also want to fully automate it. Detect, first of all, when we have these residues, for example, detect where are the residues, how much residue, and what is needed to get rid of these residues. Can we just grind it off? Do we need something else? So we want to have it more automated. And also, in fact, from beginning on, we also want to detect and automate the process of debonding as well. What kind of tool do we need? What kind of process do we need to install? This is a project going on, still in its early phase, so I hope within the next couple of years some more interesting results will be shown. And then a bit more general, concerning adhesive bonding, reversible bonding, we have lots of expertise in-house, really on the full, call it product life cycle of adhesive bonding. So it's going from the right adhesive selection, but also the right technology for your process. What kind of reversible technology, for example, would be fitted best? Is this thermal trigger needed, or can we use a mechanical trigger or whatever? That's something we have expertise in and that we are quite familiar with. Also, how should your process look like? How do we optimize the process? How also the process of debonding, what's needed, etc. So we have a lab really focused on this specific adhesive bonding process. This is, in fact, a little bit of repetition of what I just said. And there is one thing I want to highlight, because also we've seen in the former presentations also a little bit about using augmented reality in your production process, and also for bonding, debonding. It's of course an interesting technology to be used, something to support our operators in doing the right things, because adhesive bonding is quite tricky in the right processes, doing the right things on the right time, on the right spot. So using virtual reality, augmented reality in this process is quite valuable. There is a European project going on, the Smaragd project, where we want to combine digital work instructions and augmented reality for the bonding, debonding process. And we are still looking for companies that might have some interesting cases for this, where we can try some things, where we can integrate some things. So if you are one of these companies and you think, I have an interesting bonding and or debonding process, where we can look if digital work instructions linked to a mixed reality solution support for our operator, just feel free to contact me, and I will give you all information. And then we are doing much more research or upcoming research as well, using nanoparticles to optimize the behavior of these particles much more. Bio-based, debondable adhesive, of course. A lot of things are going on now around these bio-based materials, and also the use of AI, artificial intelligence, for further optimizing our bonding and debonding process and products. So also this is research getting started within a couple of months or already ongoing. So if you're interested in one of these topics as well, feel free to contact me. I will be more than happy to help you with this. And if you would have more questions later on, you don't think about it right now, always you're welcome to send me an email and to get in touch. Thank you.